let me just cut this beam just before. I'm just gonna have a slight bit of this sticking out from the wall. Okay, I'm gonna set up a coordinate system. Is there one already here? That's X, this is Y. Sure. Sure. Okay. I need to know what bending moments are here, what shear forces are here, what torques are here, right? There's two ways to do it. Way one is to draw a free body diagram of this whole thing. I have a force here, I have a distance A, and I have a distance L. Okay, now, sorry, this is a good diagram. Now, on this back wall, what's going on? Does that back wall prevent this from moving in the X direction? It does. So I need a reaction force in the X direction. Rx. What's Rx going to be equal to?
Zero.
Why? Because it's the only force acting in the X direction. How about, is it free to move in the Y direction back here? No, so I need a reaction force in the Y direction. Do you think it's going up? Yes? Is it free to move in the Z direction? No, so I need a reaction force here, R sub Z. Is it free to rotate about the X-axis?
How big's your wall?
What's that?
How big's the wall?
Let's not go there. Not free to rotate. Therefore, what do I need?
The reaction line.
And which way do you think it's going? Clockwise. Only if you're at the X-axis looking that way. It's about the negative X-axis, right? Is it free to rotate about the Y-axis? No. So I need a reaction moment here. Is it free to rotate about the Z-axis? No. So I need a reaction moment M sub Z. Okay? Anytime you have a fully fixed constraint, you have 6 reactions there. Now, when you apply equilibrium, you've got summation of forces in the X direction is 0, is Rx, and that's it. So Rx is 0. Summation of forces in the Y direction is 0. You have Ry minus F, therefore Ry equals F, right? You can do this. That's not too complex. Rz is 0. Sum of the moments about the X-axis is 0. What do you get? Where are you getting your pluses and minuses? Let's not. So you agree with that?
Yeah.
What do you say?
FA minus MX.
Did you?
Yeah.
You did say that, right?
So FA is a positive, about the positive X-axis? Yes? And MX? About the negative X-axis? So MX is equal to FA. Should MX be positive? What's a positive mean? It's in the direction that I drew it. If I got a negative right now, I'd say, how did I mess up? Because if I got a negative, I'm thinking there's no way it's going this way. So I must have messed something up there. Okay? Some of the moments about y. That's it, right? Some of the moments about z. What do I get?
L minus mz.
What'd you say?
It said L minus mz.
Is this script up? Yeah. So mz equals fl. What are these things? Here, I have this acting, I have that acting, and I have that acting. They are acting on the back end of this beam. Yes, David?
Can you explain your sign convention for MX?
No, you explain it to me.
I think it's backwards.
Oh, man, my sign convention is backwards, or my?
I think you drew the arrow.
So look, we had this argument. I had two people that attested to this. So I don't have to think about it, because look how smart they are. If I curl my fingers in that direction, where's my thumb pointed?
Negative X.
What?
Negative X.
So, shouldn't that be negative?
Okay.
It's not okay. That just means move on. How about FA? Here's my x-axis. If I start at the x-axis, go out to F, curl down the direction of F, which way is my thumb pointed?
Positive X.
Positive X. So it should be positive FA, shouldn't it? Are you happy?
Yeah, I thought that you wanted us to draw always in positive directions because you had in your other.
Ah,
one was
great,
negative.
great point there. Because I'm not writing the TK solver code right now. This will be a very big challenge for you when you do this homework. Do you want to write it all positive, or do you want to anticipate? And I cannot tell you really which is better. Okay, here's part of the problem. This isn't what I want at all, is it? Is this what I'm after, these things? What am I after? Well, yeah, but to get stress, I need moments and forces, right? Are these the forces and moments I need? Yes, no? With the emphasis on the no. What do I need? Do I need what's going on the backside of this thing?
You don't need the stress to do this in a way.
Well, not stress. I need to know what's going on here. Who is creating these things? This is. Therefore, if this is doing this to this, what is this doing to this? Equal and opposite. So here, I have, over here, what do I have? Ry is F, and that's down. I have FA acting there, and I have FL acting here. Does that make sense? I took my reactions and I said I applied equal and opposite to this cross section. Does that make sense? Now, there is another way. The danger of telling you another way is that you will learn both ways halfway and neither way all the way. I encourage you to learn both ways very well. In statics, you learn to replace an applied load with an equivalent force couple system elsewhere. So this F, I can take this F and transfer it back here. But when I do that, what do I need to account for?
The moment it causes.
Right, the tendency it has to rotate the body. it wants to rotate about the x-axis and amount FA clockwise, so I can put FA clockwise here. It wants to rotate about the z-axis in this direction and amount F sub L, right? I'm done. Actually, that was pretty fast. Do you see that? It's an equivalent force coupled system. Do you remember those words? Remember what they are? Just remember the words. It's a much faster way to do it if the loading is simple. If there are forces all over the place, then it might be better to go this other route. Okay, but now I'm to the point where I can create a stress tensor. So, if I look at point A, oh, I can't because it's time to go. But it was so fun, we were just getting excited, right? Hey, you guys want to stay another 10 minutes, 15? 10, is that a no? You, all right.